Hi guys, welcome to our Crash Course series on digital electronics. In this video, we're going to learn how to convert between number bases, focusing primarily on decimal and binary. Okay, so we're dealing with decimal and binary numbers. A number in decimal means a number in base 10. So that means that number system is going to have 10 unique digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. While a number in base 2 is going to have two unique digits, just 0 and 1. So counting this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And these are just two unique numbers. So decimal systems are the systems we're all used to when calculating. When we're dealing with digital electronics, we're going to learn how to be familiar converting to and from base 10 to base 2. Okay, so how this works is that you divide your number. If we're trying to convert from decimal to binary, you're going to be dividing repeatedly by 2 and taking note of the remainder. And at the end of the day, arrange your remainders bottom to up. So let's see how that affects us in real life. So if we were to convert 13 base 10 to binary, how we go about this is I'll first of all write 13, and then we know we're going to perform a division with the remainders. So we do a table this way, and we start off dividing by 2. So 13 divided by 2 is going to give us 6, remainder 1, and then we keep on going the same way. 6 divided by 2 is going to be 3, remainder 0. You can always check, because 3 times 2 is going to give you 6. 6 times 2 plus 1 is going to give you 13. So there's no remainder when 2 is dividing 6, but there's a remainder of 1 when 2 is dividing 13. So we keep on going. Divided by 2, so 3 divided by 2 is going to be 1, remainder 1. And when you have 1 in this final case, you divide by 10, it's always going to give you 0, remainder 1. As always, what it's going to look like. So if we count this up from the bottom up, that's going to be 1, 1, 0, 1, base 2. So 13 in base 10 is 1, 1, 0, 1 in base 2. Okay, so let's do a bigger number and see how that sort of scales up. Converting decimal to binary. So let's say we wanted to do 97. Okay, so we're looking for a number that's closest to the half of this. So dividing this by 2 and 7 by 2 is going to give us 48. Okay, because 48 times 2 is going to be 96 plus 1. So it's 48 remainder 1, since this is 96 plus 1. Dividing this by 2 again is going to be 24. There's no remainder. Dividing this by 2 is going to be 12 without a remainder. Dividing this by 2 is going to be 6 without a remainder. Dividing this by 2 is going to be 3 without a remainder. Dividing 3 by 2 is going to be 1, remainder 1. Okay, you have to take note of that. And dividing this by 2 is going to give us 0, 0, remainder 1. Okay, so reading this straight up from the bottom up is how we end up with the final binary number. So we can now say that 97 in binary is going to be the same as 110 0001. So 0001 in base 2. So that's all there is to converting decimal to binary. You perform your repeated division and you take note of the remainders. When you get to 1 as the final divisor, you're going to divide by 2 and it's going to give you 0, remainder 1, and you move up from there. So that's how to convert decimal to binary. So on the flip side, if we're to convert binary to decimal, we sort of have to look at how binary numbers are formed. So let's say we have a binary number like so. So let's say we are dealing with 1011 base 2. So if we were to look at the index of this, normally in decimal numbers we have units, place, tens, hundreds, and hundredths. But this is binary, so this is 2 to the 0, 2 to the 0th place. Okay, so that's kind of the radix. 2 to the 1, that's 2 to the 2, and that's 2 raised to the power 3. So just by knowing that these are the place values of every number, the one closest to the decimal point, the binary point, because you can still say this is 0.0, is going to be the same thing. So the one closest to the binary point is going to be 2 to the place of 2 raised to the power 0, then 2 raised to the power 1, then 2 raised to the power 2, then 2 raised to the power 3. So you just perform the multiplication, then the addition, and you go forward. So let's see how that works. So this is just going to be 1 times 2 raised to the power 0, or you could even exclude the 1 since it's unity. So that's going to be 2 raised to the power 0 plus 2 raised to the power 1 plus. So we have 0 times 2 squared here, so that's going to be 0. So we can say plus 0 plus 2 to the 3. And that's going to equal our number in decimal. So 2 raised to the power 0 is 1. So we have 1 plus 2 plus 0 plus 8. And that should be 11. So we now know that 11 in base 10 is the same as 1, 0, 1, 1 in binary. So let's go ahead and tackle a bigger number. So let's say we're given 1, 0, 1, 1, 0, 1, 1 in base 2. And we have to convert this from binary to decimal. So we start assigning. So it's going to be 2 raised to the power 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. Okay? So simplifying this, the ones that are multiplied by 0 are going to nullify, and we're going to only keep the ones raised to the power that are being multiplied by 1. So this is going to be 1 times 2 to the 0, 0 times 2 to 1. So let's bring it out. So that's 2 raised to the power 0 plus 0 times 2 to 1 is going to be 0 plus 2 squared plus 0. So that's 0 times 2 to the 3 plus 2 raised to the power 4 plus 2 raised to the power 5 plus 0 because 0 times 2 raised to the power 6 plus 2 raised to the power 7. Okay? So adding this up, so that's going to be 1 plus 4 plus 16 plus 32. So that's 1. This would have been 2, it's cancelled. 4. This would have been 8, it's cancelled. 16, 32. This would have been 64, it's cancelled. And this would be 128. Okay? So there's 128 plus 32 plus 4 plus 16 plus 1. That's 181 in base 10 in decimal. So we know that 110 1101 base 2 is the same as 181 in base 10. So that's what there is in converting decimal to binary. Each binary digit is assigned to an index of 2, right? So since this is the base we're converting to base 10, and we multiply it like so and do our addition very carefully at the end of the day. Okay? So let's now handle a sort of not so intuitive concept, and that is binary fractions. Okay, because usually when you convert binary numbers, you're usually dealing with integers. But what happens when we want to convert a binary number that has a fraction to decimal? So what do we do? So let's take a funny number, for instance. So let's say 1011 point. Okay, I think I've used that too much. So 11010. So we take a binary point. So let's say 0.01. So how does this work? How do we convert this from base 2 to a decimal? So recall we said this is 2 to the 0. This is 2 to the 1. This is 2 raised to the power 2, 2 raised to the power 3, and 2 raised to the power 4. Then the same thing is also going to apply on the other side of the binary digits, on the binary point. Okay, so since we're dealing with binary numbers, this is now a binary point, not a decimal point. It's important to take note of that. So that means this is going to be 2 raised to the power -1, and this is going to be 2 raised to the power -2. And we can perform the addition like so. We just have to make this difference. So we sum the powers less than 1 individually alongside the ones greater than 1. So if we're to do with the left hand side, so 2 raised to the power 0 is going to cancel out. So we're going to have 2 raised to the power 1 plus 2 squared is cancelling out, plus 2 raised to the power 3 plus 2 raised to the power 4. Okay, so that's going to be 2 plus 8 plus 16, and that should be 26 in base 10. So we know that the integer part of our decimal number is going to be 26. So if we were to convert the fractional part, so that's going to be 0 times 2 raised to the minus 1, which is going to be 0. So 0 times 2 raised to the minus 1 is still going to be 0, plus 1 times 2 raised to the power negative 2. Okay, so this is going to be 0, and this is going to be 1 over 2 squared, which is 1 over 4, which is 0.25. Okay, so if you add other, which is 0.25, 1 over 4 is a quarter. Okay, so if we add other parts of this binary points greater than with a 1 on them, we're going to add them to add to whatever decimal this is. But since this is the only part with a 1, this is base 10. So at the end of the day, we can just add it together. So we can conclude that 11010.01 in base 2 is the same as 26.25 in base 10. So let's do one more to get ourselves familiar with this. So let's see if we can handle 1. Okay, so let's sort of get ourselves separated. So let's say 1101.011 in base 2. Okay, so remember we're going to have to separate the part greater than 1 and the part less than 1. Okay, so this 2 raised to the power 0, 2 raised to the power 1, 2 squared, and 2 raised to the power 3. Always remember that the units place, the part closest to the binary point, is always going to be 2 raised to the power 0, not 2 raised to the power 1. So that following the binary point can be 2 to the negative 1, 2 to the negative 2, and 2 to the negative 3. Okay, so adding the integer parts, so that's going to be 2 raised to the power 0 plus 2 squared plus 2 to the 3. It's going to be 1 plus 4 plus 8, and that's going to be 13 in base 10. Okay, so adding the fractional parts, so that's going to be 2 raised to the power negative 2 plus 2 raised to the power negative 3, which is going to be 1 over 4 plus 1 over 8. So that's looking like 0.25 plus 0.125. Okay, so making this addition, that's going to give us 0.375. Okay, so let me put this in a way that's okay. 0.25, so that's 0.375 in base 10. So the final answer in decimal is going to be the concatenating, joining two of them together right as they are. So that's going to give us 13.375 in base 10. So that's all there is to converting to and fro binary and decimal numbers. Okay, it's not particularly difficult. You just have to be careful with your indices and your radix, and be sure you're correct when performing your addition. So thanks for watching. I'll see you in the next video.